Are you sure, Michael? I just asked Michael, he's an excellent speaker. It's a shame. If we have the time, I want to put you on the spot and that you speak without slides.
We overlap quite a bit, so you should just give your talk.
Okay. Davide, do I press things or this here? Yeah. My slides are up. Good morning. Yeah. So it's an educational session, and Michael has a background in psychiatry and mathematics. He's an excellent speaker, and he was supposed to give the introduction to neural field theory, the mathematical backbone. I will dive into mathematics also, but at a very particular part of the mathematics. So John asked me to speak of connectomes, connectomes of neural fields. That's his title. My title was originally a little different, but the idea is connectomes in neural field theory. Yeah? So I'm displaying here an equation, and essentially, yeah, excellent, this works. Essentially, what I will do, I will stick to this equation, unfold it, unpack it, go into mathematics, go into data, hello, Huifang, yeah, and try to connect, show you some of its concepts and key elements. I've worked in this field now for, this is the equation that John put up earlier, so I've worked in this field now for almost 30 years, and there are elements that I believe when working with brain imaging signals are important from the perspective of this type of equation and this type of approach. So bottom line is we are having neural fields, and as John presented in his very beautiful historical overview, we are dealing with quantities that are spatially continuous in space, that can be multi-dimensional. Yeah? So it can be a scalar quantity of neural activity, but there may be also other variables, so like average firing rate of a population, mean neuronal membrane voltage, etc. So, and all of this is collapsed in the vector, so in the field vector psi, given a location x and a position t. Yeah? The equation itself, the temporal evolution, is prescribed by a differential equation, so this is a time derivative, yeah, depending on a neural mass, which is the mean population activity at the location, and this John already described very beautifully, going back all the way to Boyle in the 50s. Yeah? So that's actually the equivalent. So n, neural mass at the location x. And then we have two types of connectivities. One that I wish to point out is translationally invariant, and that means shift independent. There is a symmetry, a spatial translational symmetry. In other words, the neurons that are at location x prime are their connectivity or connection strength decays in a particular way over the distance, x minus x prime, but it does not matter where they are located in space. Yeah? It depends only on the distance. This is what translationally invariant means, and that's very characteristic for intracortical connectivity. It varies from space to space because the cytoarchitecture changes, but the fact that it's depending on the distance does not change. Yeah? Which is different here, this type of connectivity, where you see does not depend on the distance x minus x prime, but it depends on the location where you are. So the activity at x prime, yeah, that travels across a distance, so this is time delay, tau, yeah, to affect the activity at location x, yeah, it does not depend only on the distance, because some areas x prime are differently connected at a particular location than at another location. This is where the white matter connectome comes in. So typically this is short distance, and typically this is long distance. Classically, this is white matter connectivity, leaving the cortex, or subcortical areas can also be included. Yeah? And this here stays typically within the tissue. Here you have a beautiful modern representation thereof. This is coming from the Jülich group, where a real brain has been sliced, 200 micron resolution, connectome representation using polarized light imaging. So all of you know this. Here you have a mathematical sketch of what I just described, where this is a long-term or long-distance connectivity, and here you have the short-distance connectivity that depends only on the distance, and then you can shift to the left or to the right. This is a 1D representation. You can do this in 2D. You can do this also in 3D if you're interested in the layered structure. But typically what you run into in neural field theory is a 1D and a 2D representation. And we have multiple, these various terms in here: local neural mass activity, very short distance connectivity, long distance connectivity. Yeah? Translationally invariant, time delay. There can be a time delay also, but because it's short distance, customarily or very often you simply drop it, which I do not do on the next slide. But what I want to do with you now is essentially go through this equation and focus at particular aspects. First element, I will focus on this particular term, and to give you a little bit of feeling. And initially I asked for a whiteboard, yeah, because I wanted to do it on the board here. It doesn't work out, so I did a little dirty on the slides here. But the idea is I walk you through the mathematics to give you a feeling for what approximations are in there, what works, what doesn't work. Yeah? And here, so the first element, what I did here is the first term. I'm replacing it, typically it's a nonlinear mass dynamics. I'm replacing it by a linear term, which will simplify some of the mathematics here. Yeah? But that is more for a perspective, because we want to focus on a perspective homogeneous connectivity. We can also ignore this term here for a moment. Yeah? So if you're just focusing on this particular term here, please recognize I kept the time delay via distance propagation in here, even though it's short. Yeah, so I put a bigger speed c in there. Yeah, but I want you to see these particular effects. Mathematically, I can pull this term out via a delta function. Here I have an integration only over space, but technically speaking, I can pull it out with a delta function, and then I have to integrate over time here also, and then replace this new kernel here by a spatial component and a temporal component. Yeah? So this expression here is completely spatially invariant, meaning it depends only on the distance in space and in time, and here again in space, which means technically speaking, when I go into the Fourier space, it factorizes. It completely factorizes. So this is a classic trick that you use in situations like this. You transform this and go into the Fourier space, and then you get an equation that depends only on k, the spatial wavelength, and the frequency. Yeah? So I'm doing this, sorry that I'm going a little through detail in the mathematics, but you never find this in the papers, very often not even in the appendices. And here, for this educational aspect, I wanted to show this to you, what it looks like. Yeah? Spatially invariant depending only on the distance. This can be the Laplace kernel, for instance. Yeah? Or something that is very often used also, the Gaussian function. Yeah? So exponentially decaying, and here parabolic, and then exponentially decaying. Yeah? So the Gaussian function. To be concrete, I'm taking the Laplacian, and now I do, I do compute for, I plug in the Laplacian in here, the delta function, and I compute its Fourier equivalent in the k and omega space, and I get this particular expression. And mathematically speaking, these operators, there are these expressions. Omega corresponds to the time, and k to the spatial dependence. I get the entire spatial-temporal properties including connectivity represented in here. And now I can do some mathematics, some approximations. Namely, I know that this distance here, we said it's short distance, so it's much smaller than the space. I can expand this and make an expansion in terms of Taylor expressions of this expression. And I get a first linear term here, and I get a quadratic term in higher order terms. But this here allows me actually to truncate this expression here. And when I take this, plug it back into the equation, and go back into the state space, I'm getting a partial differential equation here. This k squared becomes the Laplacian. The psi dot comes from this expression, minus psi, this is a linear neural mass term, plus all the other stuff that I have over here. There are some other constants in there, but I'm plugging them into absorbing them in the connectivity kernel, in the epsilon, and in the d that I can rewrite like this. So like this, coming from connectivity, we can actually derive a partial differential equation, but we cannot rewrite this particular heterogeneous global connectivity term. So keep this in mind. And the reason is, the tricks that we did, it does not depend on the distance here. We do not get rid of the time delay in here, because we have to keep this two-dimensional state space because it's translationally variant. That is a particular language. And one way to look at this is, I'm rewriting now this term that I just showed you, this heterogeneous global coupling term, as a function of individual connections, so projecting from area xi to area xj. And as before, remember there is a time delay in there, yeah? There is a time delay in there that I'm not writing. This is just the heterogeneous term times this expression here. Sorry, I did not write this here. So there is a time delay, the coupling function plus the time delay, it becomes actually a tensor, which we call space-time structure. So this is a normal connectome connecting from here to here, and this is a time, and these are the time delays. So I can actually go into the Human Connectome Project database, yeah, and I can extract the connectomes and plot the individual weights over the track lengths. And this is what you have here, yeah? Weights, track lengths for one subject, for another subject. These are just the weights, and if I plot them in the classic way, projecting from one area to the other, I'm unfolding the space, and I have the connectivity plotted over time delay. One subject, two subject, third subject, here averaged over 10 subjects, yeah? To give you a feeling for what it looks like, here I'm not having it normalized. That typically goes from 0 to 180 milliseconds. That gives you an idea what it looks like. So this I cannot approximate by an exponential function. I need to take it as is directly from the data. And what I want to do with you is work with this to give you a feeling for what the properties of the system are, and where we can make some approximations, where we cannot. Yeah. So one way to get started here is I ignore the time delays just for this discussion purposes, and I'm looking at the connectivity matrix. And here I'm making reference to a paper from the 70s, from May. This is the title of this paper, Will a Large Complex Systems Be Stable? And the idea was very famous. You have a random matrix, yeah? So you connect it very simply, and it cannot be simpler than this. It's completely linear system. Connect the system, but use random matrix properties, yeah? So Cij is a random matrix, yeah? The values in there are either 1 or 0. The values with 1, with a probability, you can scale it, C, between 0 and 1, and the corresponding inverse is for the 0 values. Then you can actually compute analytically the standard deviation, and you compute the stability of the system. You go and you compute the eigenvalues of the random matrix. Did I write them somewhere? Yeah, eigenvalues of the connectivity matrix, A plus IB. A you have here, B you have here, and because I have written -1 here, everything above A equal 1 is stable. and unstable is here, and these vertical elements provide me with the oscillatory component. Everything in this system, within this circle, every system, so every configuration that falls within this circle is stable. Everything outside is unstable. This is a very fundamental theory in random matrix theory. Now, for us, what is interesting in particular is a time delay in here for the reasons we just discussed. A very complicated matrix could be a random matrix, which it is not. But what we want to do is here simplify in order to learn some of the properties. And we have very specific tract-specific time delays. Yeah? Again, for simplification purposes to learn, we make this a fixed time delay, tau, one single time delay, but otherwise the same properties as in May's paper. Then we can go through the same dynamics and mathematics that he executed the last time, but we end up with a characteristic equation that is that has an exponential here. So we cannot solve it the way we learn, we know it from linear algebra. In fact, it becomes a translational equation. This characteristic, it's not a polynomial anymore. And the stability area, I can again compute the connectivity eigenvalues and plot them here, A and B. And it turns out it's a three-dimensional object that depends on the time delay tau that is in this system, the simplest of all possible systems, except keeping the matrix randomized. A plus B, stable in here, unstable here always, but it's this entire area underneath of this curve that is unstable. I'm cutting through here, path, to get a better impression. And please look at this. We are remaining in a linear system. Everything underneath here, stable, so that's within this cylinder. Time delay tau, and unstable here, stable here. Bottom line, in a system like this, when you're here, somewhere there, you increase the strength, you can destabilize the system and make it go in oscillations, for instance. But also, because the time delay is in there, even if you reduce the strength, you can also destabilize the system and make it go into oscillations. This is impossible in a linear system with no time delays. This is what the time delays does. Or when you're in this cylinder, whatever you do, you can never, ever destabilize the system. It's in this particular cylinder. In here, instability, instability. Very specific for this system, and you can actually generalize this. So this is something we learn out of that, and that the characteristic polynomial is not a polynomial anymore because of the time delay. An exponential function enters, and that changes the situation. You cannot approximate it away. Yeah? So that's one of the messages here. Keeping the time delays small or putting them away, ignoring them as a first approximation, is not an approximation because the behavior is completely different qualitatively. Yeah? This can be further discussed with the example of two-point connections. That's what John laid out earlier. Essentially, a two-point connection, you have a homogeneous sheet. So we're getting back now into this situation where we have neural mass dynamics, homogeneous dynamics. This one we maintain now because we will talk with neural fields, plus the heterogeneity. But the heterogeneity now, what we do is we look at only one single connection. So not a random matrix anymore, but one single connection with one time delay, which goes from one location to the other location and backwards. Mu I1 and mu 2,1. Yeah, and again with these things. If you want to write it in the way you know it from connectomics, so location y projecting into x and then plotting the connectivity strengths, so this is what you have here. These two, mu1i2 and mu2r1, you have here. And this here is the Laplacian kernel exponentially decaying. That's this, and that is there. Yeah. So, okay. I wrote this here, sorry, I forgot, yeah? So homogeneous connectivity that has a short distance. So please recognize these distances of offline, and everything along this diagonal is within the short area. So with this, you can now run simulations. And I'm showing you here a simulation, nearest neighbors, exponentially decaying, Laplacian decay, and this 1-2 point connection. I'm running the simulation. This is plotted over time. This changes also over time, so it goes to a stationary value. And now please note here, I'm changing the length, which is equivalent to changing the time delay. And it starts oscillating and showing a spatiotemporal pattern, and now it changed again. And as a consequence, now it became longer. It reorganizes itself spatiotemporally, and a longer wavelength takes over after a fairly long transient, and it becomes stationary again. Yeah? You can do this now systematically. D is equivalent of the distance, track length, or you can think of this as a time delay. And when you do this, first of all here, this is what I just showed you, the dynamics. Short, longer, very long. This is this vertical axis space, and plotted over time. It's saturated, it reorganized itself, and reorganized itself again. So that's what you just saw. And you can do this systematically and perform a parameter sweep over the distance from its periodic boundary conditions. So from here to here should be symmetric unless the system is nonlinear, and there are some nonlinearities in there because it's not fully symmetric. And please note here, for instance, at this value D, I don't know what it is, yeah? I forgot what the values are, but the only stable solution is all black, meaning resting state, 0, yeah? No oscillatory activity whatsoever. This was this oscillation you saw here, this one here. Here, the smallest change of track length or time delay reorganizes the system completely. So it's important, and that's only with one single time delay. And this is with one single time delay. And now we can start checking on the various parameters. And what has been done here in parallel, on the one hand side, what I call a reduced model is the neural field model that I just showed you. But rather than having a neural field model, you can run it also with a very high-dimensional network. In this case, it was composed of Fitzhugh-Nagumo neurons. Yeah? So very bad neurons, if you want, but still mathematically treatable. So this was a high-dimensional simulation. And 2 parameter sweeps were performed, one with this model, one with that model. And here, this is noise strength, and this is a time delay tau for the connection that was embedded in here. It's double periodic conditions, so periodic here and periodic here, or if you take this sheet, this end is connected to this end, and this end is connected to this end. It gives you a donut. Yeah? Okay, you run the simulations and you compute the degree of synchronization, and this is what is plotted here. And please note this structure here. 2 things to be noted. You have a periodic structure here that comes as a function of the time delay, number 1. Number 2, you see that there is a gradient. As you increase the dispersion that is in the parameters, the system becomes less and less synchronizable. So there's a gradient. Both behaviors are captured by the neural field model. This here is multi-10,000 dimensional, I don't remember. This here was done with a simplified neural field model and can be treated mathematically by a mode decomposition. This cannot be treated mathematically. We can go even further. This was work done by Roxana Stefanescu about 10, 15 years ago. Nowadays, it becomes possible to run this type of simulations on e-brains, for instance, using the neuron simulator. Yeah, using the neuron simulator or NEST. In this case, it was using NEST. This is one point neuron simulator. In this case, with 40,000 neurons. Same situation. Yeah. These are the boundaries. Yeah. And again, 40,000 neurons distributed here. And these are very realistic neurons, actually. Yeah. And we have the connectivity that nearest neighbor connectivity exponentially decaying, plus we have a 2-point connection with a differing weight, projecting from this area to that area. So this is a heterogeneous connectivity. This is how the connection density looks like. You can again generate different type of scenarios and perform parameter sweeps, but here in this particular case, I'm showing you two different types of snapshots of activities. This is time. You can get traveling waves. You can get standing waves. So here I'm plotting 40,000 neurons. So this is some work that has published, just been recently published by Lionel Couche et al. In Chaos. 40,000 neurons that show different types of spatiotemporal properties and coefficients of variation. When you sweep the parameters, and that's my key message essentially, we can look at this one, coefficient of variation across the time delays, yeah, and I forgot what that was, some parameter, doesn't matter. Do you see the periodic structure here? Yeah, that comes as a function of the time delay. And this you can actually do systematically. And when you translate this to the neural fields, you can actually mimic, so this is again a summary of the results, neural fields. This is using the NEST simulator, and this is using the full network of Fitzhugh-Nagumo neurons. Has to be treated computationally, can be treated mathematically, and can bias or help to develop some prior sweeps posing interesting questions. You can start introducing, for instance, to go from here to there is the equivalent of removing individual neurons. So we are talking about apoptosis, for instance, yeah, or slowing down the system in this particular directions. Yeah, so these are the type of advantages I wanted to show you, and one of the key messages I want to get across here. How can we approximate these aspects? Yeah, or which approximations are valid? Yeah. Can we throw things out as a first approximation, and with the time and the time delay, to some degree it is possible if they are very small, yeah? But in most cases, at least when you're on the full brain network scale, they are not small. When these approximations are valid, yeah, they are valid if the time delay falls into the domain of 5 to 15% of the fastest time scale that is present in the neural mass that you simulate. So if your neural mass shows locally, let's say gamma, 25 milliseconds, yeah, then 10% of that would be 2.5 milliseconds. So if the delays are larger than 2.5 milliseconds using this calculation, yeah, then then you can make an approximation. So this is again a Taylor decomposition, and you can truncate. But if it's longer than this, this doesn't work. Yeah? And that's an issue. And I just discovered a couple of days ago a paper from Mark, I'm not sure, Mark Titgemeyer and I, we were in the brain connectivity workshop on Stratey Island, and we were discussing this, and they just fixed this issue in DCM a couple of years ago, because this was exactly the integration scheme that was performed there. Yeah? And now it's a little slower, but it takes a full time delay into account. For the space, the answer is, I think, unambiguously no, yeah? Because essentially, what you could do, and this is what we were discussing, where's John? John, with the newness approximation, the exponential decay. Yeah, this was something that was done by many, including myself, in the 90s, and that's what I adapted from Paul. I had many discussions with him about this. We were missing the connectome at that time, so we approximated it by a Gaussian kernel or Laplace kernel, exponentially decaying, etc. But it doesn't take the topology into account, yeah? And the topology does matter, yeah? So it would be an approximation if there were an error term, when you, like here, when you increase the order systematically, the error term becomes systematically smaller and smaller and smaller. This does not exist, yeah? You would have to find a mode decomposition that allows for that, but at least through a translationally invariant kernel, it does not work, because the nature of the equations is completely different. Yeah? These are functional differential equations. They cannot be represented by PDEs and not approximated by PDEs, as we already seen in the context of the one single delay with the random matrix, so this toy model I showed you. Yeah? And this is what toy models are really, really good for. You gain insight of what works, what does not work, and then for the more complicated situations, you get an intuition in which direction you can go. Yeah? So for the space, no. For the time, under certain conditions, but generally not for the full brain network system. So I want to go, one element that is also important. One of the consequences thereof is that connectomics, dealing with these multiple connections, dealing with the, excuse me, technique. Where do I need to point this thing to so it works? Where's your receptor? Here? So I'll point towards you. Thank you. Yeah. When we are doing connectomics, we use graph theory. Yeah. And we deal with this type of equations. We have a neural mass, we have the connection, the connectome, and some coupling term. Now we are introducing a time delay. In graph theoretical analysis, there is no time. Yeah? We are focusing completely on this. But what we just said is in all type of discussions, determining the dynamics, at least on the large scale brain network level, the time delay does matter. Yeah? So what is a good and reasonable way to get it into the analysis? What we would like to have is a kind of effective expression like this one, which depends on the connectivity and some of the time delay structure in there, which captures essentially the space-time structure of coupling. Yeah? And coupling matters the most when you're dealing with oscillations, rhythms. And Peter will speak later about rhythms. Rhythms are omnipresent in the brain. Time delays matter there because you can shift an in-phase oscillation from in-phase to anti-phase just by having the right time delay in there. This changes completely the effects that the connectome has. So we need a renormalization for the questions where time delay matters that captures this. This can actually be done, yeah, when you make reference to Kuramoto oscillators. Yeah? You can actually rewrite this equation and look at phasings, yeah? So phasings of individual rhythms. And Joanna speaks a lot about phase-coupled Kuramoto oscillators. The delays fit in there. You can take this actually as a toy model because every oscillation for a particular band pass, you can, as long as the amplitudes do not vary very much, you can represent by this type of very generic equations. When you do this as a starting point, you can actually extract the delay and incorporate it into the coupling strength via this expression. This can be shown mathematically, so Sparse has done this together with me, and you can actually renormalize the connectome. You see for tau going towards 0, cosine of 0 is 1. You recover the normal graph theoretical analysis. You can use the interior toolboxes, etc., that you typically do. But for time delays, this becomes spectrally dependent, and you get a renormalization as a function of the frequencies that you look at and the length of the track lengths. So please have this in mind. This is actually important for the analysis and the interpretations. And in the remaining 5 minutes, what I'd like to do is I want to show you an application of these neural fields. That's my speak time that I have here. That is, yeah, okay. Yeah. So I want to show you an application that cannot be done outside of neural fields and outside of connectomics, so connectomes of neural fields, where you actually need exactly all these type of aspects. Sorry. That was, let me skip that. I thought you would speak about this epilepsy neural masses, but I'm skipping that now. Yeah. So delay constrained re-entry in neural fields. And what we are running into here is, and that's a paper by Karen et al., essentially in vitro, where multiple electrode contacts have been placed. Yeah. And you can actually, through pharmaceutical intervention, you can generate a wave propagation. Yeah? And it turns out actually that the size of the system yeah, and the connections in the system, they matters actually the dimensions in terms of propagation activity and a maximum time that the system propagates where actually re-entry occurs in an excitable system. An excitable system always has a relaxation time, yeah, in which it is unexcitable. If it overcomes that, the system can actually generate self-sustained activity completely only due to re-entry. Yeah? And this can actually depend on, as a function of the connectivity. Yeah? And this can actually nicely be demonstrated by changing the propagation speeds in the system. This you can do also pharmacologically. Yeah? And changing as a parameter in vitro, you can change the propagation speed, which allows you to provide actually, you can slow it down, you can increase it, but then as a consequence thereof, the time delays are constant that are present in the system, and you actually collapse the activity or you start generating self-sustained activity. This has been hypothesized to be a mechanism potentially relevant for epilepsy, but also observed in other systems. In the cardiac system, it has been observed. It has been observed in rat studies, and you see it here in. So this is rat, and these are electrophysiological recordings in rat and cat. And what happens there typically is that you can you click on this movie, please? Yeah, that's a movie. What happens in this type of systems? Thank you. Is the emergence of spiral waves, because it depends on the dimension of the system, yeah, and you don't have it? Okay, then don't worry. Imagine a spiral wave that is rotating, and as a function of the connectivity, it will be self-exciting due to the re-entry, or not, depending on the time delays. Pretty much as along the lines of what we have discussed earlier. Yeah? So let's take this as a starting point where we have actually a large-scale brain network with a full network connectivity, but we deal with neural fields, at least for the cortical systems, and some of the subcortical systems where appropriate. Their architectural features change, particularly cerebellum and in the subcortical areas. Yeah? And here we are taking an excitable neural mass. So has been lots of work on the neural mass dynamics of the past 5 to 10 years. And this is one of the latest generation mass models that we're using, Montbreo et al., for instance. So we are getting up to multiple tens of thousands of vertices reconstructed. The white matter connectome is extracted, tracks constructed in three-dimensional physical space, and the intersections are being computed with the individual triangles. That allows you to build a large-scale global connectivity matrix. Here, this were left hemisphere, right hemisphere, interhemispheric fibers. Here you have it written, actually. Cerebellum and subcortical projections. And then you have the intrinsic connectivity weights. And here you have a beautiful example. You're zooming in. This is all work by Paul Trebkorn in my lab, where you can zoom in and compute actually the forward solutions depending on what you measure, fMRI or EEG, MEG. Yeah? For the cortex, it works. For the subcortex, we use randomized dipoles and look only at the distance. So you get the architecture from the data. And then here you have an example of the full brain reconstruction. So this is the anterior temporal lobe in black. I need to look at this. In white, what you see here, we increase the epileptogenicity in this particular areas. It's more or less neutral in the areas outside, in the grayish areas. And then we are focusing in this particular zone that you see represented here. In blue, you see the white matter tracts that are going from the areas in which we have increased the epileptogenicity, and we can place individual sensors here that would mimic the projection data. Yeah? So these are the sensor data here, and these are the vertices. We are here in very high resolutions, and we are starting with a simulation, yeah? Increased excitability only in these whitish areas here, and propagation starts emerging as measured in the individual sensor data. Yeah? What is notable here, we can actually scale not the individual tracts and track lengths, but what we are scaling is the individual intrinsic time constant of the system, which is the equivalent, because it's a ratio between intrinsic time and time delay. So that's what we are using here to scale, in fact, plus the global gain function, the scalar gain function for the global connectivity. In these areas is where you find support for number of excitations per second propagating a particular across these individual areas. In absence of all white matter tract, you're completely here at 0. Yeah, no activity, but it's time delay induced, and in particular it depends strongly on the propagation organization. Yeah? So here you would see typically a video which, if you click on this, does that propagate? Propagate. Does that run the video? Excellent, thank you. So what you see here is some spatiotemporal organization. This is the extracted patch with a sensor array placed here. And at some point, you will see spiral waves emerging here. It starts with propagating wave fronts across this area. I'm showing here, or Paul is showing here, he did the simulations, only to the edges. Of course, it continues, but it does not integrate into the entire brain dynamics. It's actually just projects in other areas. Yeah? But here you start slowly seeing some of the spiral waves here in these areas also. Yeah? So when you now, they have a certain lifetime, a particular duration, and after a longer transient, the activity stops, number one. Yeah? Number two, it depends on the area size. Here you have 1,000 square millimeters, 9,000 square millimeters, and this is the longest time delay that the system can have in order to start generating these synchronized behavior. There's a number of excitations per second that is plotted. Global gain, time delay, in this case intrinsic time constant, but this here is a time delay. No sustained activity anywhere here in blue, but self-sustained activity here. Very, very specific. It scales actually with the area of where the epileptogenic zone size, when it increases, the tau max actually increases. And these are things now you can actually test systematically in the system. Yeah? You can actually test it systematically, and it turns out that it's actually phase dependent on certain interventions. You can perform surgery, but you can also stimulate. Yeah? And it depends on at what location in the network you stimulate and at which phase timing with regard to the phase. These are techniques that are very well known in the treatment of cardiac arrhythmias. Yeah? This phase-coupled stimulation exists. In the brain, it's never been used. Yeah? So here you see evidence thereof, but we know it from the brain that there is some evidence that it does, that it could potentially exist. This is a stimulation study in the rat, and this is a stimulation study in the human, where a phasing plot has been mapped out. Intracranial data have been stimulated in the human, and their raster plot has been built up, and the stimulation a posteriori of the phasings have been pulled out, and these are the responses of the after discharges with regard to the stimulation, and they are clearly phase coupled. So there is some evidence in there that this may work, and we have tested this now in a cohort of about 50 patients systematically. And first element what we are doing is we are looking into the scaling behaviors, namely for each patient the size of the epileptogenic zone and how it changes in terms of the minimal tau, and the seizure durations, if they scale also with the recruited tissue. And it turns out, these are predictions that come from the model, it turns out that it works actually very well and is highly statistically significant in the human as coming from the neural field theory predicted from the phasings of the connectomics-based neural fields. Yeah? So that's what I want. This is all in development at the moment, but it opens up the possibility of developing novel stimulation paradigms that are phase-coupled, that necessitate a field theory approach. With a network-based approach on discrete network nodes, you cannot do this, because the re-entry is actually the key mechanism for this. So let me stop here. I thank you. And there are two people that have contributed heavily to this, and they are also here in boldface. So at the conference, if you have questions, keep a look out for them. Yeah? Thank you very much. Yeah?